Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. Alexander Crum Brown's journey into the heart of chemistry began not in a ground laboratory, but amidst the rolling landscapes of Scotland, a land then somewhat removed from the burgeoning chemical revolutions occurring on the European continent. During his formative years, formal chemical education in Scotland presented a landscape dotted with opportunity, though also demanding of individual initiative. The available avenues for advanced study, while present, required a determined spirit to navigate. Crum Brown, possessing precisely such a spirit, charted a course that would ultimately reshape the very language of molecular architecture. His name may not resonate with the same immediate recognition as some of his contemporaries, figures who occupy more prominent positions in the pantheon of scientific luminaries. Nevertheless, Crum Brown occupies a pivotal position in the history of chemistry, particularly in the development of structural chemistry. His signal contribution lies in his elegant and intuitive graphical representation of chemical bonds, a system that provided chemists with a powerful tool for visualizing and understanding the arrangement of atoms within molecules. Complementing this, his investigations into physical organic chemistry further cemented his legacy as a pioneer in understanding the relationship between molecular structure and chemical properties. These twin pillars of structural representation and physical organic insight are vividly illustrated in his seminal papers, works that unveiled a new way of thinking about molecules. These publications served as a foundation upon which modern chemistry continues to build. It is within these papers that we find the genesis of a visual language that allows chemists to translate abstract concepts into tangible diagrams, a language that has become indispensable in research, education, and industry. Before Crum Brown's intervention, the representation of molecules was often a confusing and ambiguous affair. Chemical formulas, while providing information about the elemental composition of a substance, offered little insight into how these elements were actually connected. Imagine attempting to assemble a complex piece of machinery with instructions that only list the necessary parts, but fail to show how they fit together. This was the challenge facing chemists of the mid-19th century. They knew the ingredients, but lacked a clear blueprint for the molecular structure. Crum Brown's solution was disarmingly simple, yet profoundly effective. He proposed representing atoms as letters, derived from their chemical symbols, and using lines to represent the bonds that held these atoms together. This seemingly modest innovation provided a means of visually depicting the connectivity of atoms within a molecule, revealing the architecture of the molecule itself. This system offered an immediate and unambiguous way to communicate molecular structure. The clarity it provided catalyzed progress in organic chemistry, enabling chemists to predict, understand, and manipulate chemical reactions with greater precision. The impact of this graphical notation extends far beyond mere visual appeal. It provided a framework for understanding isomerism, a phenomenon where molecules with the same chemical formula exhibit different properties due to differences in their atomic arrangement. Prior to Crum Brown's work, isomerism posed a significant puzzle. His graphical formulas offered a way to visualize these different arrangements, explaining the observed variations in chemical behavior. Isomers, once mysterious anomalies, became readily comprehensible through the lens of structural representation. Born in Edinburgh in 1838, Alexander Crum Brown's early life foreshadowed his later intellectual pursuits. His father, a minister of the United Presbyterian Church, instilled in him a deep appreciation for learning and intellectual rigor. Edinburgh, a city steeped in intellectual tradition, provided a fertile ground for his developing mind. The Scottish capital, a centre of Enlightenment thought, fostered a culture of inquiry and innovation, a spirit that permeated Crum Brown's early education. His initial schooling took place at the Royal High School, an institution renowned for its commitment to academic excellence. There he received a broad education encompassing classical languages, mathematics, and the sciences. This diverse curriculum provided him with a solid foundation upon which to build his later specialized knowledge. His aptitude for science, particularly chemistry, became increasingly apparent during these formative years. However, his path toward formal chemical training was somewhat circuitous, reflecting the evolving landscape of scientific education at the time. He initially enrolled at the University of Edinburgh to study medicine, a common route for aspiring scientists in the 19th century. Medicine provided a context for understanding the chemical processes occurring within the human body, offering a practical application of chemical knowledge. During his medical studies, Crum Brown's interest in chemistry continued to deepen. He sought opportunities to expand his knowledge beyond the confines of the medical curriculum, attending lectures and conducting independent research. This self-directed learning reflected his innate curiosity and his determination to master the intricacies of the chemical world. He became increasingly drawn to the theoretical aspects of chemistry, captivated by the challenge of understanding the fundamental principles that governed chemical behavior. His pursuit of chemical knowledge led him to study under Lyon Playfair, a prominent chemist and public figure who held the chair of chemistry at the University of Edinburgh. Playfair, recognized for his contributions to agricultural chemistry and public health, provided Crum Brown with valuable mentorship and guidance. He exposed Crum Brown to the latest developments in chemical research, fostering his intellectual growth and encouraging him to pursue his own investigations. Despite his growing passion for chemistry, Crum Brown continued his medical studies, eventually earning his medical degree in 1858. This medical training provided him with a unique perspective on the relationship between chemistry and biology, informing his later work on physical organic chemistry. The understanding of physiological processes at a molecular level would become a hallmark of his approach to scientific inquiry. Following his graduation from medical school, Crum Brown embarked on a period of further study and research, seeking to deepen his knowledge of chemistry. He traveled to Germany, a center of chemical innovation during the 19th century, to study under some of the leading chemists of the time. This experience broadened his horizons and exposed him to new ideas and techniques. German chemistry, characterized by its emphasis on rigorous experimentation and theoretical development, exerted a profound influence on his scientific thinking. His time in Germany proved transformative, solidifying his commitment to a career in chemical research and teaching. He returned to Edinburgh with a renewed sense of purpose, ready to contribute to the advancement of chemical knowledge. He secured a position at the University of Edinburgh, initially as an assistant to Playfair and later as a lecturer in chemistry. This marked the beginning of a long and distinguished academic career, during which he would shape the minds of generations of chemists. Crum Brown's return to Edinburgh and his subsequent appointment at the university marked a pivotal chapter. He now possessed a platform to disseminate the chemical insights he had gleaned and to pursue his own research agenda with greater focus. Among the most significant and enduring contributions he would make to the field was his innovative system for graphically representing chemical bonds. To fully appreciate the impact of Crum Brown's graphical notation, one must first understand the state of chemical communication at the time. The existing nomenclature and representational methods were often ambiguous and cumbersome. Describing even relatively simple molecules could become a bewildering exercise in linguistic contortion, prone to misinterpretation. Imagine attempting to convey the structure of ethanol, a common alcohol, through a purely verbal description. The relationships between the carbon, hydrogen and oxygen atoms and their spatial arrangement were difficult to capture precisely using words alone. This inherent ambiguity posed a significant obstacle to the advancement of chemical understanding. It hindered the ability of chemists to share their findings effectively, to predict the properties of new compounds, and to develop a coherent theoretical framework for understanding molecular structure. Crum Brown's solution was elegantly simple, yet profoundly impactful. He proposed a system of graphical formulas in which letters represented atoms and lines represented the bonds connecting them. This visual representation provided an immediate and intuitive depiction of molecular architecture. The arrangement of atoms and the connections between them became readily apparent, eliminating much of the ambiguity inherent in verbal descriptions. Consider, for example, how Crum Brown's method would depict water, H2O. The oxygen atom, represented by the letter O, would be placed at the center, with two lines extending from it. Each line would connect to a hydrogen atom, represented by the letter H. This simple diagram instantly conveys that a water molecule consists of one oxygen atom bonded to two hydrogen atoms. Similarly, methane, CH4, would be represented by a central carbon atom, C, with four lines radiating outwards, each connected to a hydrogen atom, H. These graphical formulas offered a clear and concise way to represent the connectivity of atoms within a molecule, a concept of paramount importance in understanding chemical behavior. The beauty of Crum Brown's system lay in its adaptability. It could be extended to represent molecules of increasing complexity, providing a visual language for describing a vast array of chemical compounds, double and triple bonds, representing the sharing of multiple electron pairs between atoms, could be indicated by drawing 2 or 3 lines between the corresponding atomic symbols. Cyclic molecules, in which atoms are connected in a ring, could be represented by closed polygons, with each vertex representing an atom and each side representing a bond. This system was revolutionary. It provided a standardized and universally understandable way to represent molecular structure, fostering greater clarity and communication within the chemical community. It facilitated the development of new theories and models of chemical bonding, and it paved the way for the modern structural formulas that are used ubiquitously in chemistry today. Walk into any chemistry lab, open any textbook, and you will see the direct descendants of Crum Brown's original graphical notation. Beyond its representational power, Crum Brown's system also provided a powerful tool for understanding and predicting isomerism. Isomers are molecules that have the same molecular formula, that is, the same number and type of atoms, but differ in their structural arrangement. These structural differences can lead to significant variations in physical and chemical properties. Before Crum Brown's time, the concept of isomerism was poorly understood. It was often difficult to predict whether a given molecular formula would give rise to multiple isomeric forms, and to understand the relationship between structure and properties. Crum Brown's graphical formulas provided a means of visualizing the different possible arrangements of atoms within a molecule, allowing chemists to identify and predict the existence of isomers. For example, consider the molecular formula C2H6O. This formula can represent two different isomers ethanol, in which an ethyl group C2H5 is bonded to a hydroxyl group OH and dimethyl ether, in which two methyl groups CH3 are bonded to an oxygen atom. Using Crum Brown's graphical notation, these two isomers can be readily distinguished by drawing the corresponding structural formulas. Ethanol would be represented as CCOH, with each line representing a single bond, while dimethyl ether would be represented as COC. The different connectivity of the atoms is immediately apparent, explaining the distinct properties of these two compounds. The ability to predict and understand isomerism had profound implications for the development of organic chemistry. It allowed chemists to synthesize new compounds with specific properties and to unravel the complex relationships between molecular structure and chemical reactivity. Crum Brown's graphical notation played a crucial role in this process, providing a visual framework for understanding the three-dimensional arrangement of atoms within molecules. His appointment as Professor of Chemistry at the University of Edinburgh in 1869 further solidified his influence. This prestigious position provided him with an even greater platform to disseminate his ideas, to mentor aspiring chemists, and to conduct cutting-edge research. He embraced his role as an educator, inspiring generations of students with his passion for chemistry and his innovative approach to teaching. He fostered a vibrant and intellectually stimulating environment within the chemistry department, attracting talented researchers from around the world. His lectures were renowned for their clarity, rigor, and engaging style, and he was deeply committed to providing his students with a solid foundation in both the theoretical and practical aspects of chemistry. He instilled in them the importance of critical thinking, careful experimentation, and clear communication, qualities that would serve them well throughout their careers. Through his teaching and mentorship, he left an indelible mark on the field of chemistry, shaping the future of the discipline for decades to come. His graphical representation of chemical bonds stands as a testament to his ingenuity, a cornerstone of modern chemical understanding, and a lasting legacy of his years at Edinburgh. Crum Brown's influence extended far beyond the lecture halls of Edinburgh, permeating the very fabric of chemical understanding. A particularly significant area of his research explored the burgeoning field of physical organic chemistry, a discipline that seeks to understand the physical principles governing the behavior of organic molecules and the rates at which they react. At the time, chemists possessed a limited understanding of how a molecule's structure influenced its reactivity. They could observe that certain compounds reacted faster or more readily than others, yet the underlying reasons for these differences remained largely mysterious. The challenge lay in connecting the static representation of a molecule, as depicted by its structural formula, with its dynamic behavior during a chemical reaction. How did the arrangement of atoms and bonds within a molecule dictate the speed and direction of its transformations? This question formed the core of physical organic chemistry, and Crum Brown's work provided crucial early insights. He approached this problem by applying physical principles to the study of organic reactions. He recognized that chemical reactions were not simply abstract transformations, but rather physical processes governed by forces, energies, and probabilities. By carefully studying the rates of different reactions and correlating them with the structures of the reacting molecules, he began to uncover patterns and relationships that shed light on the underlying mechanisms. One aspect of his work involved investigating the influence of substituents on the reactivity of aromatic compounds. He studied how the presence of different atoms or groups of atoms attached to a benzene ring affected the rate at which the ring underwent further reactions, such as nitration or sulfonation. Through meticulous experimentation and analysis, he observed that certain substituents accelerated the reaction, while others slowed it down. Furthermore, he noted that the position of the substituent on the ring also played a crucial role, with some positions being more activating or deactivating than others. These observations hinted at the existence of electronic effects, where substituents could either donate or withdraw electron density from the aromatic ring, thereby influencing its reactivity. While Crum Brown did not have the tools to directly measure these electronic effects, his work laid the groundwork for later scientists, such as Louis Hammett, to develop quantitative relationships that could predict the reactivity of aromatic compounds based on their substituent patterns. The Hammett equation, a cornerstone of physical organic chemistry, provides a mathematical relationship between the rate constant of a reaction and the electronic properties of substituents. While Crum Brown did not explicitly formulate this equation, his pioneering work on substituent effects provided the empirical basis upon which it was built. He identified the key variables and established the qualitative trends that Hammett later quantified. In essence, Crum Brown's research paved the way for a more systematic and predictive understanding of organic reactivity. Beyond aromatic chemistry, Crum Brown also investigated the rates and mechanisms of other types of organic reactions. He studied esterification, the reaction between an alcohol and a carboxylic acid to form an ester, and saponification, the reverse reaction in which an ester is hydrolyzed to form an alcohol and a carboxylic acid salt. By varying the structures of the alcohols and carboxylic acids, he could probe the steric and electronic factors that influence the reaction rates. Steric effects arise from the spatial arrangement of atoms within a molecule. Bulky substituents can hinder the approach of reacting molecules, slowing down the reaction. Electronic effects, as mentioned earlier, involve the donation or withdrawal of electron density, which can either stabilize or destabilize the transition state of the reaction. Crum Brown recognized the importance of both these factors in determining reaction rates, and his experiments provided valuable insights into their relative contributions. His explorations into reaction kinetics were not confined to mere observation. He sought to understand the underlying mechanisms. He proposed detailed pathways for many of the reactions he studied, suggesting the sequence of bond-breaking and bond-forming events that occurred during the transformation. These proposed mechanisms were based on careful analysis of the reaction products, intermediates and rate laws. While some of his proposed mechanisms have since been refined or revised in light of newer evidence, his approach of using kinetic data and structural information to deduce reaction mechanisms remains a cornerstone of modern physical organic chemistry. He demonstrated the power of combining experimental observation with theoretical reasoning to unravel the complexities of chemical reactivity. The historical significance of Crum Brown's work in physical organic chemistry cannot be overstated. He was among the first to recognize the importance of applying physical principles to the study of organic reactions. He laid the foundation for a more quantitative and predictive understanding of chemical reactivity, paving the way for the development of concepts such as the Hammett equation and the detailed mechanistic models that are now commonplace in the field. His insights helped to bridge the gap between the static world of structural formulas and the dynamic world of chemical reactions, providing a deeper appreciation for the intricate interplay between structure and function in organic molecules. His interests, however, were not confined solely to the realm of organic chemistry. He also harbored a deep fascination with the periodic table of elements, that iconic representation of the fundamental building blocks of matter. He explored different ways of organizing the elements, seeking to reveal underlying patterns and relationships that could shed light on their properties and behavior. Furthermore, his keen intellect extended to the realm of mathematics. He recognized the power of mathematical tools and techniques to describe and analyze chemical phenomena. He employed mathematical models to interpret his experimental data and to develop theoretical frameworks for understanding chemical reactivity. This appreciation for the mathematical underpinnings of chemistry further solidified his position as a pioneer in the field of physical organic chemistry, a discipline that relies heavily on mathematical concepts and equations. He used his mathematical prowess to analyze experimental data and develop theoretical models, showcasing the powerful synergy between mathematics and chemistry. His work underscored the idea that chemistry at its core is a quantitative science, amenable to mathematical analysis and prediction. His contributions to chemistry were multifaceted, encompassing not only organic chemistry, but also reaching into the broader areas of inorganic chemistry and physical science. Crum Brown's intellectual curiosity extended beyond the laboratory, finding fertile ground in the abstract world of mathematics. He saw mathematics as a powerful language, capable of expressing the intricate relationships governing chemical behavior. His mathematical interests were not a mere sideline. They were integral to his approach to chemical research, informing his understanding of molecular structure and reactivity. He sought to quantify chemical phenomena, believing that mathematical precision could unlock deeper insights into the nature of matter. His mathematical inclinations manifested in several ways. He used mathematical models to analyze kinetic data, extracting rate constants and activation energies to understand reaction mechanisms. He also employed mathematical principles to interpret spectroscopic data, relating spectral features to molecular vibrations and electronic transitions. These analyses allowed him to make quantitative predictions about chemical behavior, bridging the gap between theoretical concepts and experimental observations. The application of mathematics provided a rigorous framework for his chemical investigations, elevating them beyond purely descriptive accounts. Crum Brown's mathematical sophistication also influenced his thinking about the periodic table. While he is best known for his contributions to structural chemistry, he also recognized the underlying mathematical patterns within the periodic system. He understood that the periodic table was not simply an arbitrary arrangement of elements, but rather a reflection of fundamental relationships between atomic properties. He explored various mathematical representations of the periodic table, seeking to uncover the underlying principles that govern the periodicity of elemental properties. This exploration, though perhaps less widely celebrated than his structural work, demonstrated his holistic view of chemistry and his appreciation for the unifying power of mathematical principles. His work with the periodic table demonstrated a broader understanding of chemistry, going beyond the confines of organic molecules. He saw the interconnectedness of all chemical phenomena, recognizing that the same fundamental principles applied across different areas of the field. This integrated perspective was a hallmark of his approach, setting him apart from many of his contemporaries who tended to specialize in narrower areas of research. As Crum Brown matured as a scientist, his influence extended beyond his specific research contributions. He became a respected educator, shaping the minds of future generations of chemists. He was known for his clear and engaging lectures, his ability to explain complex concepts in a way that was accessible to students. He emphasized the importance of both theoretical understanding and experimental skill, instilling in his students a deep appreciation for the scientific method. His dedication to teaching helped to establish the University of Edinburgh as a leading centre for chemical education. His commitment to education was evident in his development of innovative teaching methods. He incorporated hands-on laboratory exercises into his courses, allowing students to gain practical experience in chemical techniques. He also encouraged students to think critically and independently, fostering a spirit of inquiry and innovation. His teaching philosophy emphasized the importance of understanding the underlying principles of chemistry rather than simply memorizing facts. This approach prepared his students to become leaders in the field, capable of tackling new challenges and advancing scientific knowledge. Crum Brown's impact on chemistry education is still felt today. His structural formulas, which he introduced in the 1860s, are a cornerstone of modern chemistry education. Students around the world learn to draw and interpret these diagrams, using them to visualize molecular structures and understand chemical bonding. The simplicity and clarity of his notation have made it an indispensable tool for teaching and learning chemistry. This enduring legacy is a testament to the power of his ideas and the effectiveness of his communication. His structural formulas provided a visual language for chemists, allowing them to communicate complex ideas in a clear and concise manner. This visual representation of molecular structure revolutionized the way chemists thought about and studied organic molecules. The formulas made it easier to predict the properties and reactivity of organic compounds, leading to advances in areas such as drug discovery and materials science. Throughout his distinguished career, Crum Brown received numerous honors and accolades in recognition of his groundbreaking contributions to chemistry. He was elected a Fellow of the Royal Society, a prestigious recognition of his scientific achievements. He also received honorary degrees from several universities, further solidifying his reputation as a leading figure in the scientific community. These honors reflected the high esteem in which he was held by his peers and the lasting impact of his work on the field of chemistry. The recognition he received from his peers underscored the significance of his contributions and the respect he commanded within the scientific community. His election to prestigious societies and the awarding of honorary degrees served as public acknowledgments of his intellectual prowess and his dedication to the advancement of scientific knowledge. These honors helped to cement his place in the history of chemistry as a pioneer and a visionary. In his later years, Crum Brown continued to be active in research and teaching, remaining a vital force in the chemical community. He mentored countless students, inspiring them to pursue careers in science and to make their own contributions to the field. He also remained engaged in scholarly activities, publishing papers and attending conferences. His dedication to chemistry extended throughout his life, leaving an indelible mark on the discipline. His continued involvement in research and teaching demonstrated his unwavering passion for chemistry and his commitment to fostering the next generation of scientists. He served as a role model for his students, showing them the importance of hard work, intellectual curiosity, and a dedication to the pursuit of knowledge. His influence extended far beyond his own research contributions, shaping the direction of chemistry for decades to come. Alexander Crum Brown stands as a pivotal figure in the history of chemistry, a scientist who bridged the gap between classical and modern approaches to the field. His contributions to structural chemistry, his exploration of isomerism, and his application of mathematics to chemical problems all represent significant advances in our understanding of the molecular world. He possessed a remarkable ability to synthesize diverse ideas, combining theoretical insights with experimental observations to create a more complete and nuanced picture of chemical reality. His work laid the foundation for many of the concepts and techniques that are still used in chemistry today. He exemplified the ideal of the interdisciplinary scientist, drawing upon knowledge from different fields to solve complex problems. His ability to integrate mathematics, physics, and chemistry into a unified framework was a testament to his intellectual breadth and his deep understanding of the interconnectedness of scientific knowledge. This holistic approach allowed him to make groundbreaking discoveries and to shape the direction of chemistry in profound ways. Crum Brown's legacy extends beyond his specific scientific discoveries. He was also a gifted educator who inspired generations of students to pursue careers in chemistry. His clear and engaging lectures, his innovative teaching methods, and his dedication to mentoring students helped to establish the University of Edinburgh as a leading centre for chemical education. His influence on future generations of chemists is a testament to his commitment to teaching and his passion for sharing his knowledge with others. His commitment to fostering the next generation of scientists
cemented his legacy as a transformative figure in the field. He instilled in his students a sense of intellectual curiosity, a dedication to rigorous experimentation, and a passion for the pursuit of scientific knowledge. His influence can be seen in the countless chemists who went on to make their own significant contributions to the field, building upon the foundation that he had laid. Crum Brown's ability to inspire and mentor students ensured that his impact on chemistry would continue to be felt for many years to come.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.